In this episode, we're going to take a set of math ideas that can feel intimidating at first and turn them into practical intuition you can actually use when thinking about how models learn. Logs, exponentials, and the chain rule show up constantly in machine learning, not because the field loves complicated equations, but because these tools describe change in a way that matches reality. When a model improves quickly at the start and then slows down, or when one tiny change in input creates a big change in output, you are seeing these concepts at work. The goal here is not to make you memorize formulas, but to help you recognize what the shapes and relationships mean. If you can connect these ideas to learning curves, gradients, and stability, you start to understand why training behaves the way it does instead of treating it like magic. Before we continue, a quick note. This audio course is a companion to our course companion books. The first book is about the exam and provides detailed information on how to pass it best. The second book is a Kindle-only ebook that contains 1,000 flashcards that can be used on your mobile device or Kindle. Check them both out at cyber.author.me in the Bare Metal Study Guide series. A good starting point is to understand why logs and exponentials are paired together so often, almost like two sides of the same coin. Exponentials describe growth or decay that multiplies rather than adds, which is common in systems where change compounds over time. Logs undo exponentials, which means they turn multiplication into addition, and that is incredibly helpful when you want to simplify patterns. If you have something that grows like 2, 4, 8, 16, the jumps get bigger and bigger, but if you take logs, you can convert that into a pattern that grows in more even steps. In machine learning, this matters because a lot of quantities are naturally multiplicative, like odds, probabilities after repeated updates, or error terms that stack across many data points. Logs give you a way to measure those changes on a scale that is easier to interpret and easier to optimize. Now think about what it means for learning to speed up or slow down, because that is where these tools become more than just math vocabulary. Many learning processes look like fast progress early, then smaller and smaller improvements later, which is a kind of diminishing returns pattern. A log-shaped curve naturally captures that idea. Big gains initially, then flattening as you keep going. That is why you will often see logs used when modeling things like time to learn, scale effects, or the relationship between a raw signal and what the model can actually extract from it. Exponential decay captures the opposite view, where error drops quickly and then levels off, which is also a common learning curve shape. When you see training loss falling steeply and then tapering, you can think of it as a process that behaves like decay, not because it is literally exponential every time, but because that shape is a helpful mental model. Logs also matter because machine learning often deals with very large ranges, and humans are bad at reasoning across huge scales without help. If one feature ranges from 0 to 1 and another ranges from 1 to 1 million, treating those numbers naively can make the larger one dominate and distort what the model learns. Taking a log can compress that wide range so the model sees differences in a more balanced way, especially when the underlying meaning is based on ratios. For example, the difference between 10 and 100 might matter similarly to the difference between 100 and 1,000 if what you care about is a tenfold change, not an absolute jump. That kind of reasoning shows up in growth rates, financial data, counts, and many real-world signals that are not evenly spaced in importance. The log transform is like changing the measurement tool so it matches how the world behaves rather than forcing the world into a measurement tool that does not fit. Exponentials enter the story heavily through probabilities and decision boundaries, especially when models need outputs that behave nicely between 0 and 1. A common situation is that a model produces a raw score that can be any real number, and then it needs to turn that score into a probability-like output. Exponential functions are useful because they are always positive, and when you pair exponentials with normalization, you can convert raw scores into a distribution of probabilities. Even if you do not name the exact function doing it, you can still understand the role exponentials play. They amplify differences between scores so that the largest scores become much more influential. That amplification can be a feature or a problem depending on context, and understanding it helps you interpret why a model might become very confident. When you realize exponentials can magnify, you begin to respect why numerical stability and careful scaling matter during training. To connect logs and exponentials to learning dynamics, You also need the idea of a loss function, because loss is the pain signal the model tries to reduce. Many commonly used losses are built using logs, because logs behave well when you combine many probabilities. If you multiply lots of small probabilities together, the result can become extremely tiny and hard to work with numerically, but logs convert that multiplication into a sum of log values. Sums are easier to compute and more stable, and they are also easier to differentiate, which is the key for training. This is one of those cases where the math is not decorative. It is solving a practical problem of making learning possible without underflow or overflow. When you see the word log in a loss name, you can often interpret it as a strategy to turn complicated probability products into something trainable and stable. Differentiation is where the chain rule enters, and it is hard to overstate how central it is to modern machine learning. Training a model is usually driven by gradients, which are measurements of how much the loss would change if you nudge the model parameters slightly. The chain rule is the main tool that lets you compute those gradients when your model is made of layers or steps, which is basically always. If you imagine a pipeline where input becomes a feature representation, that becomes a score, that becomes a probability, that becomes a loss, the chain rule is the rule that connects how loss changes with probability to how probability changes with score to how score changes with parameters. Each piece might be simple, but the whole pipeline would be impossible to update correctly without a systematic way to link them. The chain rule is that systematic way, and it is the reason learning can flow backward through complex models. A beginner-friendly way to internalize the chain rule is to think of it as keeping track of influence through a chain of cause and effect. If changing a parameter slightly changes an internal value, and that internal value slightly changes the output, and the output slightly changes the loss, then the parameter influences the loss through those links. The chain rule says you can multiply those local influence measures together to get the total influence. This is not just a trick. It matches the idea that if any link in the chain is weak, the total influence is weak. That is why some models can suffer from vanishing gradients, where influence fades as it passes through many steps, or exploding gradients, where influence grows uncontrollably. Even without doing the algebra, you can understand the training behavior by remembering that gradients are products of many local factors. Once you see gradients as products of factors, logs and exponentials start to feel less random and more like parts of the same ecosystem. Exponentials can create very large or very small values, which can in turn create large or small gradients, depending on where you are on the curve. Logs compress values, and their derivatives behave differently, which can sometimes stabilize learning. A key idea is that the choice of transformation and the choice of loss can change the sensitivity of the model to errors. If a transformation produces outputs that saturate, meaning they flatten out near certain extremes, then the gradients can shrink and learning slows in those regions. That helps explain why models might learn quickly in the middle of the range, but struggle to improve when they become very confident or when inputs are extreme. Another useful piece of intuition is to connect logs and exponentials to the idea of relative versus absolute error. Many real-world problems are naturally about relative change, such as doubling, halving, or percent differences, rather than raw differences. Log transforms align with that because differences in log space correspond to ratios in the original space. That means a model trained on log transform targets can, in effect, focus on proportional accuracy. When you evaluate learning dynamics, you may notice the model seems to reduce large errors early and then fight over smaller proportional improvements. And that is often a sign of how the loss and transformations are defining what improvement means. This can also clarify why the same model can look good under one metric and disappointing under another, because the math is telling the model which kinds of mistakes matter most. There is also an interpretation angle that is especially important for beginners. Logs can turn a steep, hard-to-see pattern into a straight-ish line you can reason about. If you plot something that grows exponentially on a normal scale, it can look like it shoots upward and hides the early behavior. If you plot it on a log scale, patterns over time become clearer and you can compare different growth rates. In learning, this shows up when you track loss or error over many steps and want to see whether progress is steady, slowing, or unstable. A log-scaled view can make it easier to notice whether improvements are consistent multiplicative decreases or whether the training is bouncing around. This is not about making graphs look nicer. It is about matching the visualization to the underlying math of how change is happening. It is also worth addressing a common misconception that logs and exponentials are only used because the data is weird or because the model is complicated. In reality, these functions are often chosen because they encode helpful constraints and smooth behavior. Exponentials naturally enforce positivity, which is useful when you are modeling quantities that cannot be negative, like rates or variances. Log transforms can make distributions more symmetric and less skewed, which can help models that assume errors behave somewhat evenly. The chain rule is not a special trick for deep learning only. It is the basic rule that makes optimization possible whenever outputs depend on parameters through intermediate steps. If you treat these as tools for expressing structure and stability, they become less like hurdles and more like a language for describing learning. To interpret learning dynamics well, you should also connect these ideas to the concept of step size, often called a learning rate, because gradients and step size work together. If gradients are large due to exponentials magnifying differences, a large step size can overshoot and cause instability. If gradients are tiny because of saturation, a small step size can make progress feel frozen. Understanding the shapes of logs and exponentials helps you predict where gradients might be steep or flat, which in turn explains why training sometimes needs careful tuning even when the data seems fine. It also explains why scaling inputs and targets can change training behavior dramatically without changing the underlying information in the data. When the scale changes, the gradients change, and the chain rule carries that change through the entire learning process. A final connection that helps everything click is to remember that training is about pushing on parameters using feedback, and the feedback is shaped by the math choices you make. Logs can define how strongly the model is punished for being confidently wrong, and exponentials can define how strongly the model separates options when choosing among them. The chain rule defines how that punishment signal travels backward through all the internal steps, so each parameter knows how it contributed. When you watch a model learn, you are watching that feedback loop play out thousands or millions of times, and the curves you see are a reflection of these relationships. If you learn to associate certain curve shapes with saturation, decay, or compounding, you gain a practical diagnostic sense that will help you later when you compare models or interpret their training behavior. By now, the big picture should feel more coherent. Logs and exponentials are not random math decorations, and the chain rule is not just a rule you memorize for a test, but a simple idea that connects cause and effect through a pipeline. Logs help turn multiplication into addition, compress wide ranges, and emphasize relative change, which makes many learning problems easier to optimize and easier to interpret. Exponentials help model compounding behavior and create positive, probability-friendly outputs, but they can also magnify differences in ways that affect stability. The chain rule explains how learning signals pass through layered computations, which is why gradients can shrink, explode, or behave differently in different regions. When you keep these three tools in your mental toolkit, learning dynamics stop feeling mysterious and start looking like understandable patterns that you can reason about.
Thanks for listening. For more audio courses, daily newsletters, and more, please visit baremetalcyber.com.